Hello all and welcome to the discussion of COVID-19 super spreaders and how they trigger pandemics to spread from a regional outbreak to a national pandemic in India. Throughout history, we have experienced multiple outbreaks like the Black Plague, Russian flu, Ebola, and currently COVID-19. Of course, they all share one trait, they're all viral. But how did they spread so rapidly? The answer lies in what we call super spreaders. So what are super spreaders? A super spreader person sheds and transmits more viruses than an average patient does. Super spreader events are large gatherings of humans during a pandemic which might accelerate the total number of infected people. And finally, super spreader zones are the contaminant areas. COVID-19 super spreaders can be avoided by taking a few precautions, such as isolation, wearing masks, social distancing, sanitization, vaccination, etc. Gaining a better understanding of super spreaders will aid in the development of evidence-based control measures as well as the management of current and future pandemic waves. Our work employs graph signal processing tools to identify COVID-19 spreader zones, super spreaders, during super spreader events and examine the impact of these zones on accelerating pandemic in India. The preliminaries of this work include the 630 Indian districts out of 748, which we chose based on data availability of COVID-19. By computing the hover-seen distance between the nodes using the district location attributes, we constructed a geographically weighted undirected graph. The edge weights are calculated using the threshold Euclidean Gaussian functions. Because roads are the most common mode of commutation between districts, the commutation is better for nearby districts than distant districts. As a result, the nearby nodes tend to be 1 and the farther nodes have weights 0 or close to 0. This is how the graph structure depicts the relation between the graph topology and the graph signal. The daily number of infected cases of all districts from March 1st to June 10th, 2020 are stacked into columns to form a graph signal matrix. Multiple super spreader occurrences were reported, but we generally focus on 3 time periods: before, during and after the super spreader event. Now let's discuss on a couple of methods to identify these. Method 1 is total variation. Total variation on graphs emphasizes the variation of signal at the current node from its neighbors. In our work, total variation is computed for each node to its one-hop neighbors to identify the signal changes. The reasoning is that if the infection spread is smooth across all nodes, then the total variation computed between the node and its neighbors will be small. However, if there's abrupt changes, then the infection pattern in a specific node, the total variation computed is high, and which just helps us identify the superspreader nodes. After normalization, the graph signal with population of each district of 1 million residents, we computed the total variation for all the nodes to its neighbors. Then a sliding window of a week duration is continuously moved to average the weekly cases of each node. We further cumulated the total variation throughout the time of all nodes to a fixed threshold, and the threshold is calculated by taking the mean of the top 2% of the nodes with highest total variation. Using a threshold, we were able to identify the super spreader zones, and following are the results which show the identified super spreader zones in red. So using the same threshold, we determined the time varying super spreader zones. From the results, it is evident that the super spreader zones increases slowly from the March end. Multiple super spreaders are observed in the period from April, mid and May, and it decreases later. The next method is based on graph Fourier transform and high-pass filter. Graph Fourier transform deals with the translation of topological information in the signal into a spectral domain. The notion of high frequency is just that it has a drastic change with the adjacent nodes. The top 10% of the graph's replacement frequencies are used to build a high-pass filter. Now, after high-pass, the graph signal is decomposed into signal components that change rapidly with respect to the underlying graph. The HP regions have significantly different abnormal case counts when compared to neighboring districts. High-pass signals can be related with the node outbreak. As a result, it aids in identifying super spreader nodes. A procedure similar to method 1 is carried and showed in the block diagram here. So following results show the identified super spreader nodes. So the time varying super spreader zones were determined with the same threshold. The data show that the super spreader zones increase steadily from the end of March. Several super spreaders are seen between April and mid-May, and after they decline. Further research into local news articles and publications reveals that all the super spreader zones found in our analysis have concentrated breakouts in the month of April, owing to massive people gathering for electoral rallies, elections, religious festivities, and other things. So now let us use low pass filter to identify time varying spread. So we generated a low pass filter using the lowest 10% of the Laplacian frequencies to decompose the graph signal into low varying components, and the continuous sliding window is applied to calculate the weekly cumulative for the low pass components. To visualize the disease spread during the 3 time scales, data is plotted on the log scale here. And in the month of March, the virus spread is slower, and in the month of April, the disease transmission accelerates from the identified super spreader zones to their neighbors. Infection transmission finally slowed by the second week of May. Conclusions here are similarly for each node. The original data, the low pass components, high pass components, and total variation were added and the plotted in log scale over the given period. So we can clearly see that the cumulative of the high pass component show the super spreader zones, and total variation shows that. So understanding super spreaders will aid in the creation of evidence, and thank you.